Can you see anything? Can you see anything through that?
Not really.
Right, then we have to figure it out.
Screen's nice and bright.
I bet it is. Clearly need to pass something into the wall to make it go, so this can be back half. That's it, I give up. It's beyond my wit. So last few lectures, since lecture 4 or thereabouts, we've been looking at some various circuits with diodes in them and discussing their operation. And these are some general examples of a much wider class of circuits that take AC signals and change their properties using active devices. And we'll look at some circuits with transistors in after Christmas. In this lecture, I don't want to give you any more material that's examinable. I just want to do some demonstrations of the circuits that we've been looking at. But I thought I really ought to give you something to hold. So I've given you 3 tutorial sheets, which will keep you busy until the midterm, the date of which I haven't set yet, but it's often around the 18th of January. Chances are it will fall on a Wednesday because it will be in the tutorial session that we have after this lecture. But an email will go around early in January to tell you when the midterm will be. And you should expect it to be broadly about, I'm much loath to say it will be about everything we've done, because that's totally unhelpful. But potentially anything could come up, which is sort of the same thing. So it won't take you very long. I don't think you'll need an hour to do it. And there'll be some questions about circuits with resistors and capacitors, and there'll be some questions about what's the conduction state of a diode, and there'll be some questions about, or probably a question, about one of the diode circuits that we've been looking at. So if you're looking for something to revise, go through the problem sheets and make sure you can do at least halfway through the problem sheet. You'd probably be alright, but it might come down to luck. If you can do the whole problem sheet, no problem, then there won't be any problems on your exam sheet. Excellent. We good? We good? Nearly. Quick, click, 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 click. Oh, sorry. So the first circuit we looked at was the peak detector, and I came up with this diagram on the main projector, which showed something to do with the circuit and how it changes, and you get this either triangle or you get the exponential. For a biscuit, what's the cause of the exponential? Or why does it become exponential and not stay triangular? That bit, yeah? Or? Not necessarily at you. Or?
The resistance is too small.
Yes. So what are we really saying?
It's going too fast.
The RC constant.
It's time constant. So you get 3 biscuits, 2 biscuits for time constant, 1 biscuit for capacitor, and you get 1 biscuit for heavy metal. No, nobody wants a biscuit. That's how marks are distributed in exams. Think about biscuits. The reason is the time constant's the important thing. You can have a megaohm and a microfarad and get a time constant of a second, and you can have 10 megaohms and 100 nanofarads and get a time constant of a second. It's the time constant that's important. So on this, it's a pity, I take it there's no way of making it not purple. It's purple, isn't it? Alright, can you see the purple line? Is it? I'm going to write a letter to the editor then. So we've got yellow's input, and the cyan line is the current that flows into and out of the capacitor. And the meet halfway magenta line is the output voltage. So, could we put some averaging on the current? Looking at the current and the input and output waveforms with a bit of averaging, could we zoom in on the blue one, the current as well, so we can see the bit at the bottom? So this region between the 2 peaks has a slight slope, sloping from left to right. You can just about see it now, it's averaged out. And the area which is underneath the horizontal graticule, down to that line, is equal to the area which is in the peaked region, in principle. Doesn't look like it is, but it should be. Very curious. Depends, of course, where the middle is. If you look at where C3 marker is, there's actually quite a big step down from the line. It's not on the graticule line, it's where the 0 is. Can we move C3 down so it touches the line? So now the C3 ground, which is a little marker just there, so those two areas are equal. And this is the current going in, or the charge going in and out of the capacitor as the diode charges up the capacitor and then the resistor discharges it and the diode charges up again. So this is more or less what you'd expect to see, and it's what I've got in the slides. Let's have another go with the light, shall we? See if we can get in there. No? Oh well. So my next question will be, what happens if we change the value of R? What would we expect to see? What happens to these lines? I keep C constant and I'll change R. My time constant will change. Let's assume I make it 100 ohms. It's a kilo ohm at the moment, by the way. Oh, I don't know, it's around somewhere. No, 100 ohm? You sure? Yeah. What a bugger up. Really? No. Put two kilo ohms per pound. Let's make it 500 ohms instead, because I left the 100 ohms on my desk. So if I half the size of the resistor, what should we expect to see? It will. And how about the current? Oh, you could have had half a packet of biscuits then. Anybody got any advance on what happens to the current, which is the light blue line? No? Nobody fancies it. Well, we should end up with more current flowing overall. Stacking them up. They're like bitcoins, really, aren't they? You can save them or get arrested for having them. Or is it trading them? Sorry?
Save them for lunch.
For lunch? Oh, right. It's the end of the semester. Yes. Difficult times. So, if we reduce the time constant, the diode's going to have to conduct for longer, probably, to charge up sufficiently, because more charge will be removed per cycle. The diode will conduct for longer to recharge the capacitor because it's lost more charge. And this means that the current waveform is going to reduce in height, so amplitude, but be spread out in time. And overall, the area in the cyan triangle shape should get a bit bigger. Can you see that? Is that done? Oh, I missed it. Oh right, it's happened apparently. So if you look more carefully than I did, you can see there's a bit more of a curve on the magenta line in this region and in that region. And the bottom part of the cyan line should now be further below the line and a bit more spread out. What do we do next? So if we make the resistor bigger, we should observe the opposite effect. We should find that the current is more squished up in time and has a higher peak value. So that's back to 1K. Now at the moment they're still averaging switched on, so the waveforms are decaying away slowly. Done? So gone away. So magenta line is now very triangular, and the distance between the two peaks in the, or edges of the peak in the cyan line is a bit closer together. If we went to a really high resistance, a couple of hundred kiloohms, the effect would be much more obvious. But the other thing to know, of course, is the area under that line has dropped somewhat because we're adding and removing less charge per cycle from the capacitor. So we've gone from 500 ohms to a kilo ohm, 10 kilo ohms. Last one in this is 50 kilo ohms. So we should see next to no ripple, which is the change in the magenta line, and very, very small current. If I could get you to talk as well, I wouldn't have to turn up. Really? Have we changed the scale? Yeah, I don't believe you. No. No, this is 500 ohms. Sorry, I pulled 500 ohms out of the 50k box, so we're now back to 500 ohms, but made with one resistor, not two. Obviously, I planned this long in advance. Can we just see with no resistor? Because that's no resistor. Right, so this is infinite resistance. The only thing we're left with now is the charge that's lost off the capacitor, or from the capacitor, due to its own self-discharge and any leakage. So we're looking at a couple of hundred mega ohms. And we have to zoom in a long way to see the ripple. Still looks triangular, and the current, if we average it a lot, we'll see there's some tiny little sort of humps in it. Almost impossible to see. Very, very small. Almost no charge flowing. Almost all the charge is stored between cycles. Yeah, just a bit. Right. So my next question might be, what happens if we change the frequency, the input sine wave? So we're going to go from 100 Hertz to 1 kilohertz in 100 Hertz steps. So if we start off at 100 Hertz, we've got a very exponential looking decay on the voltage waveform. And also the current waveform now has a curious shape. Its diode switches on, the current flows to the current high value almost immediately. And then as the voltage on the capacitor, as the voltage on the capacitor rises up to a maximum, current decays away. It looks almost triangular. course, in this situation, the voltage waveform doesn't look triangular. And then we say that the area under that bit's still equal to the area under the spiky bit. So as we go up in frequency, or turn the aperture up, or at least down. So the output voltage now has a more triangular looking shape, and the current peak value has gone up a bit. So even more triangular, current peak value even higher. Just run through the lot. This is 400. Again. Yep. Yep. Keep going. So this is the transition from a region of operation that we dislike, where we can see the exponential in the output voltage, into a region of operation that looks like it's dropped out of a textbook, which is what I said sketch some diagrams for a peak detector. That's what I'd quite like to see, preferably in different colours, because they're very, very difficult to see. The important thing here is that the amount of charge that's being transferred is getting squished up in time, which is why the current has to be bigger. You've got to get a certain amount of charge in, and you've only got a certain amount of time when the diode is conducting, so it must therefore conduct a higher current in that period, in that part of the waveform. And this is quite difficult actually, because a lot of the time if you've got a very large di by dt, so the rate of change of current, it's much easier for electromagnetic radiation to escape from your circuit. And when it does, it will interfere with any other thing that it can come across, which is how radio works. And obviously, if you've got building a power supply or a detector or some such, you don't really want lots of EMI coming out of your circuit, because you won't get it past the FCC regulations if you're in the States, or if you're over here, GCHQ will come looking for you. But they will have read your emails, so they'll know you're building the circuit anyway, so they probably won't come. It depends. What are we looking at next? AM, good. So, after we discussed the peak detector with a sine wave, we had a look at its use as a detector of AM signals. And I think I had a slide on it as well. There it is. Value resistors then? So in the yellow we've got the input voltage, which is, actually leave it there for a minute, that's quite nice as well. Input voltage in yellow, and we've modulated a carrier, which is the higher frequency that we can see, with the lower frequency, which is the sort of wibble that's on top. And the higher frequency is 1 kilohertz, and the lower frequency is 20 hertz. And the current is still in blue, and the output voltage is still in red, or magenta, or whatever. And we have no resistor in our peak detector at the moment, so the time constant is, oh no, sorry, we do have a resistor now. Right, okay. No, that's all right. Is it? No. Right, you have to, what? Yeah, because otherwise you don't see it properly. So in the very large resistor situation, we can see the output waveform is not following the envelope on top of the modulated carrier. So we're in the situation where we've got the blue line on the main screen is the same more or less as the magenta line on the right screen. So we need to decrease our time constant in order to have our peak detector follow the waveform properly. That's it. That really is terrible, isn't it? It's quite risky. How can it be 3 degrees and can't make the lights work? So this is the right value, and it's the right value now. Why? Biscuits involved. Why is this time constant that we've got here much better than the prior one? Well, we're now on the red line on the screen is the red line on the other screen, more or less. What's important about this situation? Yep.
The frequency of the magenta line sort of matches the yellow one to the modulation, although the amplitude change in frequency modulation sort of overlaps, sort of fits in there with the AM signal.
Keep going. You're working your way towards it.
Oh, I can't do any more. That's as good as I can get.
All right. I think you've earned quite a pile of biscuits, so no more for now. The important thing is that if your time constant's too big, you'll miss out on a lot of information. In the region on this graph here, between 0.1 milliseconds and about 0.15 milliseconds, the envelope, the modulated, or the envelope of the carrier, which is the wibble on top, is falling. And if the peak detector can't keep up with the rate at which that is falling, or sort of, if you look to the peak, the peak value of one carrier cycle and the peak value of the next carrier cycle is dropping over cycles. If your peak detector can't keep up with that rate of drop, you will lose information because your peak detector is not faithfully following the waveform, input waveform. In the case of this setup we have here, even at the lowest part of the input cycle, just about here, just about there, and about there as well, we can still see there's a little bit of ripple from the peak detector. That's the critical thing. If you don't have a little bit of ripple there, your time constant is too big. So if I said sketch some ideal diagrams for peak detected AM, that's the sort of thing I'd be expecting to see. What are we up to now? So if we did make the time constant too big, how might it look? That's 10k. Have I labelled all these resistors wrongly? It can't be. Absolutely can't be. Yeah, I know I might have written on it, but I probably did it wrong. Seems like I haven't learned my resistor colour code or some such. So anyway, this is a couple of 100 kiloohms. We can see that it's very much like the blue line on the main screen. We've followed it across the top of the peak, where the capacitor really needs to gain a lot of charge. But the capacitor has no mechanism of losing charge because the resistor is very, very big. Time constant far too long. So it doesn't follow the waveform in the region where it's decreasing on a per cycle basis, sort of 0.3 milliseconds through 0.4 milliseconds. So this would not give you a faithful representation of your original signal when you demodulate it. Where are we now? No more. So the other circuit which we've been talking about for quite some time is the clamp circuit. And who wants to hear about the clamp circuit again? Anybody want to hear it a third time? It does cause a lot of difficulty. No, everyone is completely happy with the clamp. I'll put it on the midterm. Don't you make me. Well, if I keep going through this lecture, there should be... There it is. So there it is, just while it's being set up. We had voltage source, and capacitor, and a diode, and a resistor. And we said, well, I'll use that one because it's nicely drawn. First half cycle, this bit's bigger than that bit, and the only thing that can happen now is, firstly, there is no charge here. There is no charge in this capacitor because I've decided that this whole circuit's been switched off for a very long time. I come in first thing in the morning, having been away all night, it's been switched off for ages. There is no charge in the capacitor. If there is no charge in this capacitor, there can be no voltage difference across its plates, because the stored charge is proportional to the voltage difference. Q is CV. If I've got no Q, it doesn't matter how big the C is, there'll still be no V attached to it, or across it rather. So, no voltage here. And if that's the case, and this is doing that, this must do the same. Because if there was some difference in these two, that would imply a voltage drop, but there is none. So they must be identical. And that situation persists for the whole of the first half cycle, so that's towards 0.5 milliseconds. Thereafter, this waveform starts to drop. So in this situation now, this end is more positive than this end. And we can have some current flow, because when this end becomes 0.7 volts more positive than this end, guessing none of you can see that, can you? That's what it looks like. 0.7 volts facing down, which is the same as minus 0.7 volts there. So we are just below the line, just below the centre line in the blue waveform. In this situation, because this has still got no charge, this should be close to whatever this value is, and I'm calling this value my reference. So I'm saying this is 0.7 volts above this, facing that way, which is the same as this is 0.7 volts below this. It all depends how you like to think about it. Anyway, the upshot of all this 0.7 this way, that way, is we end up with 0.7 volts across the diode in the direction which will cause it to conduct, which is 0.7 volts on the anode greater than the cathode. And once we've got that, we'll have some current flow around this loop, and charge will accumulate on this capacitor. And you could say, all right, some charge has to leave this plate as well, but how you want to think about it is neither here nor there. Some current flows into this capacitor and is stored as charge, and that results in a voltage appearing across it in this direction, because this is the plate which is more positive. And that voltage will rise up to whatever the input voltage is minus the value of the diode. So that's 0.7. So we are now in the region where we've charged up the capacitor, and if we could see capacitor voltage, which we can't, but if it was there, we'd see capacitor voltage has gone up by the difference between the bottom of the blue line and the bottom of the black line, which is just above. So the capacitor is now charged up. And at some later point, oh there it is, the the diode will cease conducting, and it will cease conducting because there will be no more current flowing into the capacitor. The capacitor will become as charged up as it can be, given the voltages which surround it. So the current will cease, and that will cause the diode to switch off. It is not a case that the voltages become such that the diode switches off. It's the capacitor finishes charging up as much as it can, the current ceases, and that is the switch off of the diode. Eventually, we'll come to, or we won't come to, but with some other lecturer you will come up against some circuits with inductors in and diodes, and then the case of what exactly switching off means will become quite critical. And then you'll really be forced to think, why does this circuit behave this way? Because it won't be as neat as it is with capacitors and diodes. But for now anyway, capacitor's charged up, and this voltage, input voltage waveform starts to rise again. And as it's rising, we must have some change in voltage here as well, because the diode is not conducting, so I can say, well, it's not there. And I have to go back to my original situation where the resistor is quite large and it can't change the voltage on the capacitor very much because we can't take enough charge out to make much difference. So there's no change in charge, there's no change in V. I, C, dV by dt, where Q is the integral of I. So if this one's rising, here, going up like that, wow, that was bad, like that, do it again. This one's doing that, this one must be doing this as well, except that there is now a voltage difference across here equal to the peak value of that minus the 0.7 that we lost in the diode. So this waveform is now shifted up the page a bit. In fact, the lowest part of this waveform, lowest part of that, must be held at minus 0.7 volts. And on the screen behind me, that is almost exactly the situation that we find ourselves in. It may not be very apparent from the diagram. Can we DC couple the output? That's better. So, yeah, just pull that out. If you look at the yellow waveform, you must be quite careful when you read the oscilloscope like this. The yellow waveform reference, that's to say 0 volts for the yellow waveform, is where the little marker is on the left that says C1, which is about 3/4 of the way up the screen. And the yellow waveform is symmetrical about the marker. That's to say, it spends half of its life above the marker and half of its life below the marker. So this is regular AC with no DC offset, or no appreciable DC offset, not more than a few millivolts. Are you cold? Hangover? Feeling sad? Have you caught his cold wherever he's gone? Where's my... Ah, you're very close, you see, you're probably going to die before too. Just think you wasted your final days listening to me. Thanks. So, we've now got the situation where the input, which is in yellow, and the output voltage, which is in red, have the same ground reference. So we can compare them just by looking. We don't have to worry too much about what's above and below the line. And we can see that it is shifted up, because in the case of the magenta line, minus 0.7 volts is where it's a bit flattened on the lowest part of the cycle. And in the case of the yellow line, that's also where minus 0.7 volts is. And in this region we have the diode conduction. Now, the way this circuit's actually rigged up over there, we are not looking at the charge change in the capacitor anymore, because that's a trickier thing to measure in an environment where mistakes are seen by everybody. So what I've done is I've measured the diode current instead. So we're not seeing a slope in this region here between the two peaks, because we're not looking at the charge going in and out of the capacitor anymore. We're now looking at the charge in the diode. What I've secretly done is I've got my diode and I've put a little resistor in there, and what I'm showing is the voltage across there. So as the diode conducts some current, we'll drop some voltage there, and that's why it's facing down, whereas in this case it's facing up, because I'm saying the current's flowing that way, we're expecting to read this voltage. Only problem is current and voltage now in the same direction, so what we actually need to see is that, but what I'm plotting is that, and as far as the scope's concerned, the current does that, which is not the case. The current actually goes up. So what we've got is a minus sign, which is why there's a minus sign on the board, on the screen. It's flipped over. It doesn't matter really, it's just to show you what the wave shape should look like. Can we have a look at some AM? We're a bit tight.
Thought one every 4 minutes would be a bit tight.
So just before it appears on the board, if I had some AM in my peak detector, what should it look like? Any takers? Well, you missed a chance. Never mind. So there we've got some AM at the top, and this is the same AM signal that we had earlier. It's 1 kilohertz. Is it 1 kilohertz? Doesn't matter if it's not. It's not quite the same AM that we had earlier. In the prior example, we had 200 hertz carrier, which is the high frequency in the middle. In this case, we're up to 1 kilohertz. But the modulation is still the same. We still have 20 hertz frequency, which is carrying the information, which is the longer period. And we can see that the output, which is in purple, is held at minus 0.7 volts at its minimum. So it's shifted upwards. Not only is it shifted upwards, the depth of the distance between the highest point and the lowest point is now double what it was before, because we've essentially got a ruler and sort of pushed all the little waveforms up to make them level, which means the difference which we saw on both sides before, we would see some difference like I'll shift it up in a minute. We had an envelope like that before with an envelope like that afterwards as well, and then we had in here some business like this. Well, if we measured that to there and that to there, in the case where everything shifted up, this distance here and this distance here must get added together to yield a new waveform, which is where that bit's flattened, and this height is the sum of this height here and that height there. So really we've just shifted everything up a bit. Is that the last one? That's the last one. Right then. Any questions? None at all. That's pretty good going. Needs a bit of time to filter in. Right, well we've got a problem class now in St George's, so if you run you might need me down there. But if you really run I might give you a biscuit.